So, welcome to everyone. Myself, Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering, Hyderabad. Today, I am going to discuss about role of nanotechnology in semiconductor optoelectronics field. So, this is the second part of this topic. This discussion is the second discussion about for this topic, semiconductor optoelectronics topic. In my first video on this topic, means role of nanotechnology in semiconductors optoelectronic, I already discussed some primary features of nanotechnology, why the nanotechnology important, what is the nano scale, okay, all these things. So today I am going to discuss about some more thing about role of nanotechnology in semiconductor optoelectronics, and basically I will discuss about why the abrupt change in the properties of nanomaterial will occurs. Okay, what are the main reason, so that once you go from bulk material to their nano counterpart, the property will be abruptly changed. So why such things happen? What are the reason behind this? Okay, so reason behind the extraordinary properties of nanostructure. Okay, what are the reason behind the extraordinary properties of nanostructure? So basically there are two primary reasons. The first one is surface to volume ratio. Surface area to volume ratio means let's suppose this is your nano object, okay, and if this nano object have a surface area S and total volume V. So this S by V will be considered as surface to volume ratio. So once you move from, this is your nano for suppose X material. Now same X material is also available in bulk form, means every dimension of this material is greater than 100 nanometer. So now calculate the surface to volume ratio for this same X material for its bulk form. So again you can calculate the surface area and volume of the material. So surface to volume ratio will be always high once you go in the nano region. Okay. Surface to volume ratio means, suppose if there is available assembly of 100 big bricks, okay, now these bricks are accumulated at one place, 100 bricks, and these bricks are kept over one by one. Now you can calculate the volume of this assembly and also surface area of this assembly. Now just what, for example, just I considered the accumulation of 100 bricks, and in material science these bricks you can consider it as atoms. Now you reduce the number of these bricks to 10, and what happens? Accumulate at one place. This is second layer, then again third layer. What happened? In that case, all the bricks, when it is available in the number of 10, all the bricks are now available at the surface of this accommodation or this accumulation. But once you consider the 100 bricks, some bricks are available inside this agglomeration. Okay, means that bricks are not available at the surface. But here number is less comparison to 100, but all the bricks are available at the surface, means surface to volume ratio. Obviously the volume is also less comparison to this bulk form, or 100 bricks. If you are comparing 100 bricks to 10 bricks, and these bricks are placed at the single place at once, so for 100 bricks, obviously surface area and volume for such assembly is greater than comparison to this accumulation of 10 bricks. But if you are calculating the ratio, surface to volume ratio, S by V, so this small assembly of 10 bricks will be always greater than this 100 assembly of bricks. Surface to volume ratio of this small assembly of 10 bricks will be always greater than surface to volume ratio of this 100 assembly. What does it means? Once you are, so you can compare, this is as a bulk material, this is at a nano material. So once you move from bulk to nano, your surface to volume ratio will be increased. Means whatever the atoms or molecules are present in that nanostructure, that atoms or molecules, most of the atoms or molecule will be always available at the surface of that structure. Now, all the atoms are free to react, free to respond over any signal or over any activity. But let's suppose in this bulk case, those atoms are those bricks, analogy. Bricks are now here analogy with the atoms. So now those bricks are present inside this assembly or accumulation. Those will not react in such extent comparison to those bricks are available at the surface, or those bricks are available at the surface of this assembly, or those atoms are available at the surface of this assembly. So comparison to those atoms are available in the core or inside of this assembly will not generally respond for any signal or any reaction. Okay. So, but here, whatever the atoms are present in the nano region or nano scale structure, whatever the atoms are available, all the atoms are available at the surface of that structure. Means all the atoms will respond, react, okay, will take a part in reaction. So if the surface to volume ratio will be less, high, less in the bulk form, but once you move from bulk to nano, surface to volume ratio will be high. So if the surface to volume ratio for any structure will be high, that structure will be more reactive. Okay. So more reactive means then they will show more conductivity, more optoelectronic behavior or anything. Okay. So that's why the reason behind the extraordinary properties of nanostructure. This is the question. So what will be the reason? So the first thing is surface to volume ratio. Now second reason behind the extraordinary properties of nanostructure is quantum confinement. So what does it mean, quantum confinement? Confinement, confinement means restriction. Let us consider one structure and there all the possible three dimensions. Okay. So let's suppose this structure is grow in this x direction beyond the 100 nanometer. In y direction also beyond the greater than the 100 nanometer. In y direction also greater than the 100 nanometer. In z direction also greater than the 100 nanometer. So this structure is what? This structure is bulk. Now anyhow you restrict the growth of this crystal so that this crystal will not grow beyond the 100 nanometer. So what happened? This, let's suppose I am imposing the restriction in along the x direction, so that my crystal will not grow or cannot grow beyond the 100 nanometer. So this x direction or this x dimension will be less than 100 nanometer. Now in x direction you impose some restriction, means you confine the crystal. Your crystal cannot grow up to certain limit. So these things are quantum confinement. Now what is quantum confinement? The quantum confinement is once the wavelength here, what is this crystal? In this crystal number of atoms are present. They are trying to move in every available possible direction or every possible direction. So you know that in quantum mechanics, the concept of de Broglie wave or matter wave. So if any matter particle having mass m and try to move or moving with velocity v, so a kind of wave will be always associated with such type of particle, and these waves are known as matter wave or de Broglie wave, and wavelength of this wave lambda is equal to h upon p, momentum of this particle, because this particle is in motion. So if confinement region will be, means this restricted area will be comparable to the wavelength of the matter wave associated with these electrons. So such type of restriction is known as quantum confinement. Okay. So, and those materials are even known as quantum material, not even nano material. So confinement and quantum confinement, even if you are confined the material, means you are restricted the growth of that material in any particular direction. So what happened? If you are keeping low and low any particular dimension of the material, so for with the help of quantum mechanics you can analyze the corresponding energy level E is equal to n square h square upon 2m, and length or dimension of that material in that particular restricted dimension, means L square length. So if this L is very small, the corresponding energy values will be high, because E is inversely proportional to L. Okay, E is inversely proportional to L. So if L is very low, your E value will be high. Okay, so quantum confinement, once you restricted too much your material, even 1 to 3 nanometer range, so your electron wavelength, matter wavelength associated with electron, means wavelength of matter wave associated with electron will be comparable to your crystal dimension. Then such type of confinement is known as quantum confinement, and in that case these energy levels will be so high. Okay, and in that case your material will be considered as quantum material. So these two things, surface to volume ratio and quantum confinement, these are primary reason behind the extraordinary properties of any nanostructure. So the quantum confinement trap of the particle and restrict the motion. Okay, the particle cannot move, whatever the electrons available inside the particle cannot move beyond the certain restricted portion. So this is a kind of confinement. So quantum confinement produce a new material behavior and phenomena. The density of state and corresponding energy levels will be changed, and engineer confinement control for specific application. So suppose you want some higher band gap value in particular direction. In those direction, if you confine the growth of the material, the corresponding direction, the energy band gap of the material will change. So they will show the different optoelectronic behavior. So based on your requirement, you can engineering or tune the material based on your requirement. So there are three possible type of quantum structure. Quantum dot. Quantum dots means all the three direction is now confined. Okay, means your material cannot grow in all the three directions. So that particular kind of nanomaterial is known as quantum dots. If material can grow in only one direction, the other two direction is confined. Such type of things looks like a wire. So you can say that is nano wire or nano tube. So that type of thing having two dimension restriction and one dimension growth. So nanowire is a nanowires or nanotubes are kind of one dimensional particles travels only along the wire. The quantum wells now here the particle your matters can grow in all the two direction but restricted in one direction. So it looks like a seed, plain seed, or you can say it is a thin film, a kind of very thin film. So such type you can say that is a quantum well or in potential well type of structure. Your two-dimensional sheet or thin film is a kind of potential well structure where the particle can move in two direction, but one direction is confined. Means your structure can grow in two direction, but it cannot grow in rest direction, means third direction. So what type of structure you are able to see? That is a kind of two-dimension seats. Okay. So based on these things, your density of state. See here, this is the density of state variation in bulk case. Means three-dimension structure bulk case. This is the two-dimension structure. Density of state variation. This is the one-dimension structure. Density of state variation. Now in quantum dots are sharp energy levels. No such type of variation. Okay. In two-dimension structure, a step-like function. Okay. So all these things here discontinuity happen. A kind of Dirac delta function. Okay. A sharp peak is available in density of state variation. So same thing. Confinement direction. So these are the in nano seeds, two dimension. Okay, in these direction, your material can grow, but in this direction, you are confined the material. So quantum well or thin film. So one direction confinement, but two dimensional electron system. So this is a kind of seeds. Okay. Another one, two direction confinement. See, confined in two direction, but this is your confinement direction x and y. But your electron can flow, your material can grow in rest means x direction. If confinement direction are ny and nz or kx or ky, but your material can grow in x direction. So you can say this is a kind of one-dimensional electron system where the confinement direction is 2. Now, 3-direction confinement and 0-dimension electron system. This is a kind of perfectly quantum dots. Okay. So, surface to volume ratio, more electrons will be available on the surface so that your material will be more reactive. Means if you are going from bulk to nano region, more available of atoms, all the atoms are generally available at the surface of nanostructure. That's why all the atoms will take the participation in reaction or any they will respond for any signal. So the properties of nanomaterial will change due to surface to volume ratio increment. Due to quantum confinement, I already discussed what is quantum confinement. See here, with the help of quantum mechanics, you can discuss the particle confined in a certain region x is equal to 0 to x is equal to a. This is a kind of potential well, infinite potential well. So you can calculate the energy of this particle. So this is the energy formula. So once you are increasing the mass, see, if mass will increase, the density energy levels is now decreasing. Okay, mass of the particle is increasing, the energy levels are now decreasing. What happens if this region of confinement will decrease? The available energy value of this same particle will increase. Okay, and these are the density of state variation for bulk to quantum dots material. So in bulk material it is vary by root E. In quantum well it is constant. Okay, in quantum wire it is vary for 1 by root E, and in quantum dots d. Okay, now see here, once it will move from bulk to nano. In bulk, this is your band gap. Okay, once you are smaller your particle confinement width, what happens? See, band gap is increased for same material. Why this band gap is increased? Due to why? Because this A is decreased. Confinement width is now decreased. So for same material, the band gap is now changing. So same material is look like orange, yellow, green, then blue. So same material is now showing the different colors, a kind of orange, yellow, green, then blue. So see, the optoelectronic response for the same material once you move from bulk to nano is now changed. So surface to volume ratio. So once you took the very small piece of nano objects and having around 0.1 mm. So what happened? If you are divided this 1 meter cubical box into 0.1 mm cubical box. So in this case, around 2.5 acres surface area is available. But in this case, only 6 meter square surface area is available. So see how much surface area is available once you go from bulk to very smaller object. Obviously 0.1 mm is not a nano regime, but even if you go for nano regime, the surface area is become 100 crores. Okay, so now all the atoms for considered nano region are all the atoms are available at the surface, so they will react more comparison to their bulk counterpart. So this surface to volume ratio is generally considered by 3 by R. So surface to volume ratio, as R decreases, surface area to volume ratio increases, so the properties of the material will be changing. The material has high surface energy if it is small in size or vice versa. As the surface area to volume ratio increases, the materials possess good catalytic property because all the atoms are now available at the surface. Thus, the nanoparticles show enhanced stability and broader scope of application. In some cases, materials that are inert in their larger form are reactive when produced in their nanoscale form. This affects their strengths or electrical property. For example, a particle of size 30 nanometer has 5% of its atom on its surface. At the 10 nanometer, 20% of its atom, and at the 3 nanometer, 50% of its atom available at the surface. Means once you are moving from bulk to nano, the available number of atoms at the surface is now increased, so they will more reactive. Okay, so now there are some techniques to prepare these nanoparticles. So the broader classification for preparation of nanoparticle is top down and bottom up approach. In top down approach, you will consider the bulk material. You initially you have to choose the bulk material, then crush into powder form, then further crushing. These powders will come in the nano region, means up to 100 nanometer, 1 to 100 nanometer. Now, in bottom up approach, you have to choose small, very fine atoms, and their size are, when you can't control, but anyhow you have to work. Your starting point of view will be atoms are molecule. Anyhow, these atoms are molecules will ac- accumulate at one place, agglomeration. Okay, so they will create some clusters, nano cluster. These clusters will further join with each other and comes in the nano region. Okay, so this approach, once you are started, or your initial point of view will be atoms are molecule, and with that you are reaching to nano region. So this technique or this approach is known as bottom up approach for getting the nanoparticle or nanostructure. If your initial material or point of view is in bulk form and you are approaching from this bulk region to nano region, so this approach is top down approach. So these are the possible mechanism for getting the nano material by top down approach. So the first is ball milling, the second one is physical vapor deposition, the third one is chemical vapor deposition. In bottom up approach, there are several techniques, but I am mentioning here only three: the sol gel, precipitation, and combustion method. So, with the help of these, you can prepare your desired nano. With help of these techniques or possible ways, you can prepare your desired material in nano region or nano scale, and you can get the desired property with that nano scale a nano region particle. So I covered all the things. In that way, the nanotechnology will help in semiconductor optoelectronic field. So thank you.
Like, share, and subscribe. Hit the bell icon for more updates.